Swayam Prabha. Digital India. Educated India.
So let's look at instead of an cyclopropene, let's look at an aziridine. Say an R. This is this, right? And one more example is now tell me how many electrons would be involved in this particular case if this ring opening has to occur. Previously some group was leaving, so you are generating carbocation. In this case, when you heat it, there is no group is going to leave, but there is a nitrogen has a lone pair. Exactly, and then the sigma bond, you will have a 4 electron getting participate in the reaction. It will go through an and 4N type reaction under thermal condition, and 4N means a Kahn rotation. Then what will be the product here? Kahn rotation. Remember the same thing. The Kahn rotation means same direction, right? Both clockwise. The one which is out below will come out. The one will above will also go out. So that means you would get CO to Me, CO to Me. This is a product. Okay. Fine, no? So of course you have to put in this way. Rather, I would probably draw it like this. It's more meaningful instead of putting a dot. Now, for the below one, again and 4N, but however, we look at a case this way, and once again we do the same direction. The one above will go out, and this side above will come inside. So that should give the product which is so where we can identify this relative stereochemistry. If you do a further cycloaddition reaction with this particular 1,3 dipole and the resulting stereochemistry, we will be able to identify how this opening has occurred further from here. Okay. So that's an additional thing. So we can also do this with an instead of this kind of system, we can also do it with instead of 3 membered, we can also go with an 5 membered ring. That's where the Nasaroff cyclization comes into picture. Say, let's take such a kind of system. So pentadienyl cation, like an allylic cation. Now we have pentadienyl cation. Of course, I placed it purposefully at the middle instead of at the terminal, so that we will have a way we show the reaction easier. Or we can also have. So previous case, all that we have seen, all of them are an even number of carbon. The last 2 cases we are seeing is in an odd number of carbons. Here is the 5 carbons. It could be a cation or it could be an anion. Now once again we can use the same funda to say that because how many electrons are involved here? 4 electrons, right? So that means this will fall under a 4N category. How many electrons are involved here? 6 electrons. So this would fall under 4N plus 2. So under thermal condition here, so this would be undergoing a disrotatory mode. Here an photochemical Kahn rotation, and the same when you go here, a thermal Kahn rotation, photochemical disrotation. Remember that. Okay, so it can give what will be the product here if that reaction occurs. whatever way it is, the reaction occurs, there will be a five-membered ring. Because this being a cation, the new bond formed, you will have an allylic cation as a product. Yes, I am not showing in how the cation forms. So, we are starting with the cation. That means the resulting thing, so if you wanted to push this way, you push it here. When you are breaking this, you are going to have a carbocation over here and then push this way. Which means actually the way I have written, but if you want, you can see that this before cyclization, you would have a structure like this. This I made like a resonance structure this way. Same if you wanted to go here, you can once again push it this way so that you can go to an anion this way. Of course, you cannot push it to an anion site, right? You can do push from an anion, create a bond and then generate an anion. So, this should give basically an allylic anion, which you can write as a resonance structure, resonance hybrid in a form of like this. So, here you have to add a nucleophile to quench, here you have to add an electrophile or a proton to quench, either way. Let us take an example where we often see this kind of reaction is from a carbonyl derivative. For example, dienone. Okay, and you have dienones of this type. If you treat this with an acid, say phosphoric acid or any acid for that matter, and heat. So, what kind of reaction are you expecting here? You would potentially have initial protonation, right, either in the form of oxonium or for my convenience, I am not writing in oxonium. Obviously, oxonium will be more stable, but I am writing for my convenience for looking at an electrocyclic ring closure, I am writing a carbocation over here instead of writing an exactly oxonium ion. So, now how many electrons are involved? 4 in electrons under thermal condition. What kind of mode of cyclization is supposed to occur? A Kahn rotation. If it is Kahn, you go by this. So, you push it this way, a same direction. The one proton will go down, other proton will come up. So, you would have the product like this. This is going down and then this is up. Then you would have, because the way we are going to see the way I showed you, if you push this way, then you have a carbocation over in this particular carbon. Am I correct? Now, the product is from here. Either I can lose this proton instead of adding a nucleophile. The easiest one is intramolecularly the losing a proton and forming a double bond, which is rather easy. Okay, one is I lose a proton here, or I lose a proton from here. There are two possibilities. If it is A, and if we consider this B, if it is by an A, if it goes, I would get double bond over here, and then let me make an enol only, then I can make a corresponding ketone. Okay. So, this would further go up. The keto-enol tautomerism can make an ketone. This as a product. Okay. So, this reaction is called Nassarov cyclization. Have you guys heard of this term? Nassarov cyclization. But if it goes by B, what will happen? The proton going to be lost here, the double bond would form in this particular fashion. Retaining an proton state chemistry over here, and for the ketone tautomerism can make a ketone. Obviously, you know that this is going to be favored then at this, because for this ring, this olefin is in exomethylene. Okay, exomethylines are not very stable. If it is in an endo for this, for both the ring, this double bond is in endo. This is in exomethylene for one of this ring. This is not going to be favorable. However, if I start with an methyl group, for example, if I start with the methyl group instead of a proton over there, say if I start like this, if I get a similar intermediate like this, instead of proton I have a methyl group, then I do not have an option to deprotonate from this side. Am I correct? So if I react this with an acid, then I would end up getting a situation like this, where an Me here and then we have a carbocation, we have an enol, and the only possibility here now is the hexamethyl. There is no option. So in this case, the product has to go through this way, and there you get only this product. Okay, either a bronzed acid or Lewis acid also can do the reaction. There is a silicon directed chemistry is also known. For example, what is the nature of silicon? Where do you use? Say, let me take a very similar structure. Okay, and I take in one more without silicon. If I treat with an iron chloride, since I said Lewis acid, I taken an iron fluorescent and activating reagent, so that I get a carbocation, which is pentadienyl cation what I get, and that would potentially say, let me draw the structure, then we will have an clarity. Right? And iron will have supposed to have minus there, no, so plus in this. Now, this cyclization I can do it in two ways. The way I have been saying only one direction, say for example, either I can push it this way and generate a carbocation over here, or I can push it this way, carbocation, and this side. So when you do not have a silicon, the carbocation formation over here is going to be where it's going to be more favored. Say, I'll go with the color. I'm not putting any stereochemistry over here. My concern is different. Which one do you think will be formed? The pink? Sure, right? Because this is an tertiary versus a secondary. Obviously, this will be more favorable, and if that is the case, you would end up getting a product which is this. That means obviously this is a proton which is going to be lost in this case, and I am directly writing a product which is this. But when you have a silicon, that is interesting. What is the nature of silicon? Silicon would tend to stabilize a beta carbocation. Okay, silicon stabilizes a carbocation at the beta carbon. For example, if I go by this, so for this silicon, so this is an alpha position and this is a beta position. So that's why we call them silicon directed Nassau cyclization. Because of silicon and which has a ability to stabilize a beta carbocation, now the push will be at this way where you generate carbocation like this. Here I need a stereochemistry because of a Kahn rotation, right? And then that is going to occur. I would have the carbocation over here, silicon Me3 over here, and then an OH. So there is a proton here. Okay. So now the silicon, because there is a Cl in the system, not OH, here would be NO, NFe, Cl3 minus. So the chloride can take up silicon. That means any X minus can come in, take a silicon and push the double bond over here. Okay, and that would give as a product which is a completely different than what we have observed before. So this could be mostly they say trans, but it could be a mixture of cis and trans because it's a enol kind of protonation. So you can potentially have it from both the sides. You can have both a cis and trans. So look at here. In this case, when you do not have a silicon, in this case we did not have. In this case we have. Look at the product. When you do not have, the double bond orientation is very different. When we had, the product orientation very different. Overall oxygen state, everything for the system is same, remains the same. However, only thing you see that because the carbocation stability is what is drives. In this case, the tertiary versus secondary what you are looking at. Of course, here is also again a tertiary versus secondary, but secondary has a better stabilization by a presence of a silicon. That adds in more support and that results to a completely and different product further. All right, so we can actually, I think I have given you guys most of these things. There are a lot more examples which you can go through. I'll only take you to guide to an 8-pi system, and we can, from there, I'll try to go to one cyclodation reaction. I have not got any questions from you guys. You are able to follow? The sound is very less. Early morning energy is less. I suppose to be more. So we will go with one more example with an 4-pi systems, 4 double bond systems, and once again, kind of, but then open chain systems. So tell me now quickly the product. Both under thermal condition, what would be the product? Make it fast. First one will be trans. Okay. The second case. So she says the first one is a 4 and 8 electrons, so it's a 4 end system, a Kahn rotation. The methyl groups will be, because the Kahn either this way and this way, so the methyl group has to be a trans in relation. And this case again same 4n and con. So once again if you do, both will can go down or both can come up. This is an interesting example. So now what happens if I further heat this? Further heat this. You can have 4n plus 2 this rotation, right? 4n plus 2 this rotation. I can have a cis member ring with a ring junction being cis. Okay, we can further do this. Okay, let me ask you one more thing. Here we use a linear catalyst. What is linear catalyst? Alkane to alkene. What do you use? Alkane to alkene, yes, you are right. You use a palladium, hydrogen and some poisoning, either barium sulfate or quinoline what is used. Am I right? It does not over hydrogenate your product. So, a linear hydrogenation when you do, what will be the product is a question. Alkenes, that will be similar to this. Am I correct? Because Professor Nicola has used a very similar strategy to build a natural product. Of course, there is not a methyl group at the terminal carbon. They will have a couple of carbon and then a diene or dienophile kind of system. It has a very different outcome. In a single step, he forms a tricyclic structures so beautifully. Just only what he has done is a linear hydrogenation of this, that's supposed to be cis selective or trans selective. Selective to cis product or trans product? A cis product, right? Both the alkyne will get hydrogenated in a same phase, that the results to a cis alkene. This is what we mentioned. That's the requirement we said initially. When you have multiple intervening double bonds, all of them has to be cis. Then only we can have electrocyclic ring closure. Okay, so that this if you do hydrogenation, it comes here and further it goes to this and moves over here and followed by, if you have a diene or dienophile, you will have a very interesting 4 plus cycloaddition reaction to form and macrocyclic tricyclic strictures. Okay, so I will give you a few examples so that you guys can try it, right, quickly. So, when you heat, see what kind of product you can get. In the other case, try to explain this mechanism. It is a labeled oxygen. When you heat, it goes to like this. You see what are the other things which can be possibly happening. Okay, so I give you 3 examples. One is this, when you heat what would happen. Other is I wanted to explain the mechanism where the star refers to a labeled oxygen, say O18 for example, right, is the labeled oxygen. So there is a kind of the one which was the part of a carbonyl has become a part of the ring. So I want you to explain this and also see what kind of product you can get over here as well. So I am not asking you guys to do it now, please make a note and then practice it. So, with that we will move on to a cycloaddition reaction. Shall we? Cycloaddition. So, what are the things which you know as about cycloaddition? Make it fast. You don't have time. Di-dienophile. In other words, make it simpler. Di-dienophile is very specific system. That's like disorder reaction. What you are talking about, 4+2 cycloaddition reaction. There's a di-in and dienophile, right? In other words, you have a two polyenes undergoing a cyclization. It's a bimolecular reaction. Very generic thing is, previous case what we have looked at, electrocyclic ring closure or ring opening, it's a unimolecular transformation. A cycloaddition reaction is a bimolecular transformation, where two conjugated polyenes comes into form a new product, cyclic product. Okay. So, in that process, you will generate a 2 sigma bonds in this case. Say it can be simply 2 alkenes can lead to a cyclobutane as a product. Okay, this is one of the basic example. We will worry about whether it is allowed under thermal condition or photochemical condition afterwards. Okay. And the other case what he has mentioned is about a di-in and dienophile, giving you here a cyclohexene as a product. Once again, the way we discussed before, if you wish, you can push this arrow to form a product where the bonds are broken and where the bonds are formed. Okay, same here as well. You can start pushing in arrows this way, so that you will be able to draw the structures. When you look at a relative reaction, I mean, a related reaction with respect to electrocyclic ring closure, what we have said, where butadiene and hexatrienes are forming a product, there we had a 1 double bond extra. Am I correct? It was a cyclobutene as a product and cyclohexadiene as a product. Remember this. But in a bimolecular transformation, you have 2 bonds formation, 2 sigma bond formation, and here these 2 are going to be formed. So, what does this mean? In your system, if you have a cyclobutene, then you can think about an electrocyclic ring opening. If you have a cyclobutane, then you can have a reverse of reaction. This is also once again a reversible transformation. So, when you say the forward reaction is a cycloaddition, right, that is what we are discussing now, and the backward reaction is called as either a retrocycloaddition I think I missed one C here, or cycloreversion, SION, okay. Either reversing basically, right, cycloreversion or a retrocycloaddition, what we can call it. Okay, retro means is again going back kind of stuff. In the product of whatever is formed, or in this case are called in general cycloadduct. Very generic term. Cycloadduct means the result of a cycloaddition reaction. In any kind of structure can be called as a cycloadduct as long as the reaction is through a cycloaddition. Okay. So, this is a typical examples of a cycloaddition reaction. So, what are things which we said? It is a bimolecular reaction. You have to have a two conjugated systems has to come in, and when the reaction occurs, you will have 2 sigma bond formation, and if we count the overall number of double bonds in the product, you will have an n minus 2 double bonds. For example, you start with an 2 here, so there is 2 are gone to a sigma bond, so there is no additional double bond going to be there in the system. You start with the 3, you are left with the 1, and 2 sigma bonds are being formed. The reverse reaction, as we said, this is also a reversible reaction, and like an electrocyclic ring closure and ring opening transformation, This is also reversible reaction, which is we classify them as an either retrocycloaddition or a cycloreversion as a case. Now, what are things we supposed to see next case is to see how these reactions are going to occur. In an electrocyclic ring closure, we directly went to some kind of stereochemistry and then started explaining how this reaction can happen, right? And then we looked at a homo-lumose, particularly homo in this case, unimolecular reaction. We looked at a homos, and then the mode of cyclization. We said under which condition this is favored and all that. Now, this being a bimolecular transformation, there are two alkenes or two polyenes are going to come into picture now. In both the lobes in both alkenes, the lobes either on the same phase or an opposite phase can react potentially. So that is what he was asking on the other day about a suprafacial and anterofacial transformation. For example, that's something we need to understand first. A suprafacial, which means, so when you have a homo or lumo, does not matter. I am just drawing a very simple structure, right? I am not drawing any lobes here. Okay, if this is a plane what you are looking at, right? This is a plane of, this is a plane of your sigma bond. You have above and below a lobes, for example, right? Of course, actual molecular will look very little different. Now, if the interaction of this particular polyene with and one more polyene where the reaction occurs, for this polyene, if the interacting ones, let me put it this way, because these are the one which is reacting, right? Interacting. If the lobes which are interacting on this polyene are on the same phase, then you call them as an suprafacial. It could be either both on the top, both on the bottom, does not matter. It has to be on the same phase. Now, an anterofacial is very simple, very similar to that. Okay, once again, if you are looking at a plane this way, okay, so if this interaction at one end of the lobe, it interacts with a top phase. If the other lobe, on the other end, it interacts from a bottom lobe. This is called as an anterofacial approach. Okay. Now we have a two coupling partner. That means two polyenes are going to react, and we have two approaches. How many variations we can have? Now, we have a coupling, there is a polyene 1 and polyene 2, let us say, right. Say the first alkene, I am just making it pretty simple, right. So, we have a lobe, okay, you are able to see this, right. This is in one polyene, right, and I can have another polyene So, I am placing this plate just for you to differentiate it. Actually, I should even place this even a better way to make you feel even better. Let me redraw this one more time. Because the carbon-carbon bond, the chain of an polyene is going to be in a plane of the sigma bond, right. So, that means, if I put a plane like this, then I would have it in the part of the plane, that the whole thing also be, the chain also will be part of the plane. Okay. Okay. This versus the same over here also. Like that. Okay. So now this is going to go actually below and this is up. So now if these two interacts and these two interacts, for this, those two lobes which are below the plane, which is interacting with an other alkene or an polyene on the above the plane. If you consider for this particular polyene, this is supra. We will shorten it. When you consider for this polyene, this is also a supra. Okay. So this is one example, one possibility where both polyenes interact in a suprafacial mode. Now I think about the next case where one interacts suprafacial, other interacts in anterofacial. Okay, which is kind of difficult to draw, but however, if you are looking at one alkene, that means you have to have another one coming perpendicular. So that this kind of wave open interaction has to be there, which is little difficult, right? Geometrically, it's going to be very challenging. But I'll just show you how I mean, without a plane of whatever I've drawn, I'll just show you this way. You have one. So in this case, this interaction, in this case, and this interaction. I'm sorry, both I put under. Okay. For this polyene, the same lobes are interacting. For this polyene, the opposite ones are interacting, which means for this polyene it is supra. Okay, here is supra, and here it is antra. That's what we are supposed to know. But as I told you, if this is the way it has to interact, you have to have one polyene, which is a phase which is this way, means other has to come and perpendicular to this, so that you can have an interaction. But if the smaller system of this, what we are looking at, although symmetry wise what we are going to see, you may see that they are can be favorable, but however, geometrically this is going to be forbidden, because you cannot approach such interaction in a smaller molecule. Very larger ones which is still possible. What is the other option? Both are antra is possible, but both antra is, in other words, both supra is also again possible. We'll see an homolumos, then we'll understand even better, and how does this kind of and explain in supra. So that means you can have three possibilities potentially. You can have supra antra, and antra. But then, as you said, an antra if really feasible, then actually it can be supra also can be possible. We'll check that particular thing. So now to understand this, under which condition, which mode of reaction would occur, we need once again to know. Again, we can use all those three strategies which we have discussed, right? Like which I mentioned to you before, like symmetric correlation method, right? Transited aromaticity method, frontier molecular method. All this can be used. We will go with a rather simple and FMO model. Okay, so FMO, what does it say? In a unimolecular transformation, we said obviously to form a bond we need an electron. So we took only the HOMO to consider. Now we are looking at a reaction between two different molecules. Two bonds are being formed. So it's rather better to look at a HOMO of one molecule, a LUMO of the one molecule, because that's where you're going to from one to another. You are going to give a share and then take back kind of stuff, right? So it's better to choose an HOMO of one, a LUMO of another one. Once again, the 2+2 cycle addition which we looked at, right, giving you a cyclobutane. This is a 2 pi electron system, and this is a 2 pi electron system. Am I correct? And giving you a cyclobutane. Now, what will be the HOMO and what will be the LUMO which we have to look at in this particular case? under thermal condition. Let us take it for the condition which is a thermal. So, under thermal condition, we take a HOMO of one alkene, a LUMO of another alkene. HOMO of an alkene, ethylene. For ethylene, HOMO is what under thermal condition? Psi 1. Okay. So, psi 1 will have a 0 node. Am I correct? S, which is a LUMO? Psi 2. So, psi 2 will be having an 1 node. Now, if I aim to do a suprafacial interaction here, guys, listen. If you aim to performing an suprafacial approach for both an alkene, then what would happen? In one case, I would have a bonding interaction, right? However, this is not a bonding interaction, because somebody would call it an anti-bonding interaction, but then is not an unbonding interaction. Can you create a bond here? No. Which means, what are you supposed to arrive at here? That two alkenes, two ethylene are simple two alkene cycloaddition under thermal condition is a disfavored in an suprafacial mode. Understood? If it is supra when you consider, this is supra here which you are considering, and this also I am considering supra, and this is disfavored. Okay. Let us look at the same thermal condition. Now, I am looking at, so as we said, this is a HOMO, which is psi 1, it is a LUMO, psi 2, which is the same thing I am extrapolating here. Now, if I look at a supra in this and antra in this, right? The supra, for this I interact on the same side, yeah, I get a bonding, right? And supra from here, antra from the other one, I still get an bonding. So, I will have both ends bonding in nature. So, this means under thermal condition 2 pi plus 2 pi cycloaddition is allowed under thermal condition via a supra-antra interaction. Okay, the reaction mode has to be as supra-antra, it is favored. This is what I meant. So, consider now a situation that the only two carbon atom, where in one phase it has to react in the same side, other it has to react in another side. How will you be able to do that? Which is practically geometrically not a favorable situation. That is why a thermal 2 plus 2 cycloaddition of a simple alkenes are not possible. They may be symmetrically allowed based on the discussion what we had FMO model. As symmetry wise, this process may be allowed, but geometrically it is forbidden. So, hence, a 2 plus 2 cycloaddition reactions of an alkenes are not a favorable transformations. Okay. There are other thermal transformations, we will come back hopefully if time permits. So, now let us look at a photochemical condition, same under photochemical, under IGNOU. Under IGNOU, what will be the HOMO? Psi 2, the HOMO will be psi 2, right? LUMO, here this is challenge. So, we need to understand that when you shine a light or when a photochemical condition, is not that all the molecules are going to be always in an excited state, right. So, you take obviously some will be a ground state, some will be excited, and the alkene alone is a challenge in this particular case. You take one which is an excited one, which is a HOMO, which is psi 2 when you take it. So, that would look this for an alkene which is an under excited state, right. There that is an electron got transition, there the HOMO. Then obviously the larger amount of molecule will be in the ground state. There the LUMO will be, it's again, no, psi, LUMO can never be psi 1. Psi 1 can never be a LUMO. Okay. What will be the LUMO? I am talking about this is the molecule which are in the ground state. Is supposed to be alkene. Alkene can never have a psi 3. Psi 2 only, there is only two, the pi and pis are only, psi 1 and psi 2 only. So, that is in the LUMO of a molecule in a ground state, if you look at it, that is also, right, that is also a psi 2. Remember, only thing what I said here, this is star I have put, which means under the photochemical condition, you are looking at a molecules which are in an excited state, the electron transition happened. In those molecule, you have a HOMO which is psi 2, and you cannot find a molecule in the same everything in an excited state, right. It will obviously it loses energy and comes back. So, you cannot maintain everything in completely in an excited state. So, some of them will be in a ground state, that ground state LUMO when you look at, which is also psi 2, and now when you look at the interaction, again suprafacial, supra when you look at it. So, from this means this direction here and here. So, these two and these two will be, both will be a bonding interaction, which means 2 pi plus 2 pi cycloaddition reaction. Under photochemical condition, it is an allowed. Okay, a thermal it is a not allowed process. Photochemical condition it is allowed. If you look at an supra antra, geometrically itself we said not possible. We look at whether symmetrically allowed or not. Okay. Supra antra for example. So, here it is supra and here is antra when you take, right. That means you will have an one side and a bonding, and this side is not an bonding interaction. Hence, that is not a favorable thing. How about antra and antra? We told no, an antra is actually coming back to an supra type, right. That means here I can have an antra which is like going from this different phase to a different phase and coming from another side, which you will obviously you have to rewrite these structures such that you will have an antrafacial interaction. I have to reorient this and then write. It will eventually look like eventually you can go back to an suprafacial stuff. You understand, no? So, that means I place it this way. I'll draw it for you guys. So, conveniently forget an interaction we have placed. Now, this I place it differently. Both are psi 2 again. Now, look at, okay, this is also antra, this is also antra, I am going to look at it. For this alkene is also antra, for this alkene is also an antra. That is why from here you cannot do it, you just have to flip that by MO and then you will realize that an antra also is possible. So, that is what I mean. When you have an antra possibility, I am sure you will have a supra possible. So, that is why this you do not really count at all. So, you will only worry about the only two approaches, one is supra and supra antra. So, now we are going to kind of throw this guy out, saying a supra antra, although geometrically it may be favored, symmetrically it may be favored, geometrically it is not the favorable approach. You cannot approach such a smaller things possible from here. Now, how will you do it for a 4+2 cycloaddition reaction. So this is 2+2, right? So now, if you wanted to say this nomenclature of this transformation, in an alkene of this type, what we say, in one case is 2 pi, and other case is also 2 pi, and then you give a subscript as a supra, as an S, other subscript as a supra, and cycloaddition if you represent, it's complete, which means there are two alkenes reacting. A 2 pi means there's more 2 pi electrons and 2 pi electrons basically reacting. That means two alkenes are reacting. In which mode? Both of them are reacting in an suprafacial mode. If you come to this, you write like this as an 2 pi S plus 2 pi A. The subscript of S and A represent and mode of reactions what you are talking about. Now, we will quickly go on to an 4+2 and diene and alkene. So, that becomes this becomes an 4n system, that becomes a 4n+2. We can once again summarize and extrapolate it from there. Okay. So, now when you take a diene and dienophile, this is a reacting partner, you call a class here the dienophile, diene and dienophile, as you rightly said. So, this is diene, this is dienophile. Okay, maybe best an H there. Okay, dienophile. This resulting to, I'm sorry, cyclohexene. Cyclohexene as a product. Now, let's look at once again at a thermal condition. So, thermal condition, both obviously in the thermal condition, there is nothing one need to worry about. So, now you would see a HOMO of one will take and LUMO of another thing will take. We always consider here the normal condition, diene will take it HOMO, dienophile LUMO will take it, and we will also take a reverse and explain that this is the observation holds good. Okay. So, diene a HOMO of diene is a Psi2, correct. So, that will have one node, very good. So, there is a one node here, a Psi2. LUMO of dienophile, I will say alkene instead of writing big one, which is also Psi2. Sorry, ma? Aha, mama, correct. This one we have made it. Okay, you are right. Because there is only one node we said here, no? You are right. You are right. Okay, otherwise you will not be able to make a supra interaction. Okay, so here Psi2, which is also Psi2, which will have a one node again, and this is an way you have. Now, we look at an HOMO of a diene and LUMO of a dienophile, and these are the interaction. Now, let us look at a supra, a supra for this and supra for this also, which means you have here a bonding and you have here also bonding. What does this mean? Exactly. So, if you look at a 4+2 cycloaddition reaction or 4 pi or 2 pi cycloaddition reaction is allowed under thermal condition via suprafacial mode of reaction. Okay. So, a supra-antra will not have any meaning, right? Once again, we are not going to consider that because geometrical constraints. Let us look at now, I wanted to show you a reverse is also possible under thermal condition. A LUMO of an, although we prefer to use, we will come back to an electronics when it come. When you say LUMO of dienophile, diene, LUMO of diene is what? Psi3 under thermal condition, right? A ground state, Psi3. So it's supposed to have how many nodes? So 2 nodes. So right, this time is correct. Okay. So and then an HOMO of diene. Dienophile or alkene will write. Alkene is better. Which is psi HOMO, no, under thermal condition, psi1. So that will be now let's look at a suprafacial interaction. Right, here supra and here supra. You will realize that this also can result to bonding. So we need not worry about which HOMO I take, which LUMO I take for normal discussion. When it comes to substituted version, then we will worry about electronics. When it comes, we will worry about how this can be and oriented. All right. So what does this mean? This means that under thermal condition, and 4+2 cycle addition would occur at an through an R4+2 suprafacial interaction. Okay. So this how we will represent as an 4 pi s plus 2 pi s a cycle addition reaction. What about a photochemical condition? The next point is supposed to be a photochemical condition. Photochemical condition, obviously one molecule you have to take it as an ground state, other molecule in an excited state, what we are going to see, right. Let us take first diene excited state and dienophile in a ground state. Okay. A diene excited state, what will be the HOMO? A HOMO of diene in, and I put a star to differentiate this. Okay. So which will be psi3, which is supposed to have how many nodes? 2 nodes. All right. Did I try it correctly with the 2 nodes? Now let us take a LUMO of a dienophile in a ground state. Obviously, both being an excited, even more. See, one molecule is difficult, but both having excited is probabilities are very less. So now we look at an LUMO of a dienophile in a ground state. What will be the case? A LUMO of diene. Alkene. Every time I write that. Alkene, which is psi2. Not psi1, but psi2. LUMO, no? So which means you will have 1 node. Now if I look at a suprafacial, okay, in one case you will have bonding interaction, and on the other case you would not have this. Of course, if you look at, I can also reverse the way I have shown. If you go with an here excited state, you will have again an psi2, right? HOMO of this in an excited state will be psi2. Here you are looking at a LUMO of a ground state will be psi3. Then when you see it also, you will not have a proper interaction coming into picture. Okay, so you would have that mismatch in things, and you see in one side excited and the other side not excited state. If I missed it incorrectly, you just make sure that you cannot have both of them in an excited state situation. One in a ground state, one in an excited. That way only you combine. Otherwise, both in excited state, you will still see a suprafacial things, which is not actually, and probability wise it don't be very high. So which means this is not going to be an allowed process. However, the same if you have to look at an antra, in one case supra and other case antra, I can still get a reaction. So if you want to, as a whole, like we summarized for an electrocyclic reaction, if you want to summarize for a number of electrons involved, okay, with respect to mode of reaction, let's not worry about a mode of reaction. We'll say we'll only okay. Let's keep that because some case it's supra and allowed. So mode of a reaction, okay, and then we say condition. Okay, a thermal and photochemical. My handwriting becoming very bad. Okay, so let's take 4N. In a 4N, if it is suprafacial, thermally it is 4N, not allowed. Okay, or disfavored you can put, right? Not disfavored. Photochemically it is favored. So I will probably now write a tick mark rather than writing a whole thing. Okay, so here I will cross this and here I will put a tick. Same 4N, supra intra, thermal condition it is, it's supposed to be favored. Photochemically it will be disfavored. Now, same if you look at it with respect to 4N plus 2, supra, thermal condition will be favored, photochemically it is disfavored, as supra intra, thermal condition will be disfavored, photochemically it will be favored. This is what I was telling in the beginning itself, that some of this interaction may be symmetrically allowed, but however geometrically they will be forbidden because you cannot have such an approach possible in a smaller systems what we are looking at. Okay, so which means you will be pretty much concerned about only this, that means 2 plus cycle addition mostly under a photochemical condition, and a 4 plus cycle addition is under thermal condition. This is all what you mostly look at it. An exception for an thermal 2 plus cycle addition is with an ketenes, allenes, isocyanates, where you have an sp hybridized carbon in the middle. So that gives an thermal cycloaddition reaction. Remember, a ketene, allenes, isocyanates would still give you a thermal 2 plus cycloaddition reaction. However, it is not a normal alkene. The approaches are very different because, for example, ketene, when you look at it, the center carbon is an sp hybridized, and allene, when you look at it, center carbon is sp. Isocyanate, center carbon is an sp. Nitrogen and oxygen, center you have a carbon. So all this, because the homo-lumo for this allene, ketenes and all that, when you look at it, the shapes are very different, and homos and lumos and interaction, where perpendicularly you will see that an homo is in one direction, the lumo will be perpendicular to that. So that's why you have an better approach, because I do not have time to explain all those examples to you, but I wanted to bring your attention to that case, that all this you can extrapolate from here and go on writing in many examples. If time permits, I will come back. If any vacant slots, I will come back and then we can probably discuss examples for this, because Diels-Alder reaction has a much more interesting thing, where there is a 6th rule, endo rule, why an endo, what is Regis selectivity, and electronic substitutions, why this has to happen. All these are also interesting. If there any slots available, I will come back and then we will discuss those examples afterwards. Okay, but remember, take this as a basics understanding, use this and then see how we can arrive at the product, how we can predict the product out of the given substrates. All right. So thank you. If you have any question, please go ahead. Okay, if there are no questions, we will close it here because already it's going to be 11. So you have your tea, coffee, and then come back for the next session. Okay, good guys. Thank you.
SwayamPrabha. Digital India. Educated India.